Hello and welcome again, this time to our second live stream in regards to the clean energy transition. I'm Sebastian. I will guide you through this live stream today, and I'm teaming up with Lerato, and she will share her expertise about pre-concentration and alternative processing routes with us. So good to have you.
Thank you very much.
Something is important to point out. Water and energy savings are existential issues for today and for future generations. And in this live stream today, you will hear about a new way, or why a new way of thinking about pre-concentration can help to manage these mentioned challenges. And it's good to have Lerato. She's STEINERT's Global Mining Applications Manager, and she is the expert when it comes to sensor-based sorting in mining operations. Good to have you.
Thank you very much for the wonderful introduction again. I'm really happy to be here today and to be discussing this important topic. I think that today we'll take a deeper dive into the technology, and we'll be able to understand a little bit more what alternative processes are available to pre-concentration, and understand also why that is important to apply them.
And we definitely want to get you involved, engaged, so please feel free to ask your questions. You can write those questions in the chat and we come to those questions, and Lerato will answer those questions with her expertise after our approximately 15 minutes talk. Now some more information about Lerato to further introduce her. She's a qualified metallurgical and materials engineer. She has over a decade of experience in minerals processing. That's important to point out. And yeah, as we can tell from the first live stream, none like her can bring complex issues to the point so briefly and easily. So once again, a pleasure having you.
Thank you very much.
All right, so we are discussing these topics here because the clean energy transition, as mentioned, is upon us. And the mining industry has a key role to play in the transition occurring responsibly. And Lerato, yesterday in the first session, we heard that the mining industry can make a huge difference in saving water and energy. So to get this one here started, can you please refresh our minds on some of those figures that you already mentioned yesterday?
I think absolutely. I think it's important to reflect on the global perspective. We as an industry from mining, we're not isolated. We have an impact on the globe, and that's very clear. In order to understand this, or to get an understanding of where we're impactful, a lot of studies have indicated that global energy consumption from mining activities, or at least the attribution from mining activities, is between 3 and 4%. That's quite a high number. And further studies from various different sites have indicated that approximately 30 to 40% of the energy consumption on mines and minerals processing plants is generated from comminution and crushing practices. These are important processes. They reduce the size of material, they liberate the mineral that is of value that we're wanting to extract. So this is an important process. However, if we have the opportunity to reduce this energy consumption on site between 10 and 30%, this will make a very large impact on the global consumption. If we reflect back on those figures that I mentioned, we're looking at somewhere between 1 and 2% of global energy consumption is from these processes. So that gives us an understanding what kind of an impact we could have from reducing. The other thing that is quite alarming for me is around water, and this is something that you mentioned as well. In terms of water consumption in the minerals processing sector specifically, it's alarming to see the kinds of figures. Around 250 million liters of water is used to produce a ton of gold. In arid regions, this is extremely problematic, and we have to think about what ways we can try to find to reduce water impacts and water consumption impacts from minerals processing and mining activities.
So I have to stay with these numbers that you mentioned in the end. It's 250 million liters of water to produce 1 ton of gold. So it's obvious that something has to change. What are you suggesting the change to be?
I think that we need to think about minerals processing in a slightly different way. We have to think about adapting innovative technologies and thinking where we can apply two very important things. First is dry processing, where it's possible to apply dry comminution, for example, dry crushing in the way of HPGRs, but also to apply dry pre-concentration. And why pre-concentration is so important is it offers two things. One is to do coarse or perform coarse gangue rejection fairly far upfront in the process. In that way, we are eliminating a portion of waste that doesn't necessarily have to be processed further down. It doesn't have to be mixed with water. It doesn't have to be crushed further down. And at the same time, we are reducing the amount of water that needs to be mixed with it. So it's a twofold aspect. If you can perform it dry, you are avoiding additional water. And if you can reduce the amount of material that is down into the process, then you're also relieving energy consumption. So very important.
All right. So one could say, yeah, that's easy to share here and to say, but wouldn't it mean that mines would have to abandon tried and already tested processes?
I can understand where that idea or that argument may come from, is why try something new? But important to point out is that sensor-based sorting or pre-concentration using sensor-based sorting doesn't require anything new. This is adaptive technology that doesn't require anything more than a simple crushing and screening plant, which is what you require for standard wet processing, like jigs, like dense medium separation. So we need to think of adapting our flow sheets to include these kinds of innovative practices. And we need to also remember that adaptation means we can also remove certain aspects or reduce certain aspects, so reducing water reticulation systems in that way. And that helps downstream on the tailings management and on the slimes management side of things, which is very important to point out. Like I said, it's adaptive technology. And as we know, we have changing ore compositions, we have changing grades, and sensor-based sorting is something that can adapt very well to these kinds of changing conditions. So from STEINERT's perspective, we have over 100 global installations spread across the world. And as you can see from these images, this gives you an idea of what this looks like. Important also to point out from an operational perspective is that not just environmentally, but operations-wise, sensor-based sorting on the dry basis, when compared to other wet processes such as dense medium separation, has an OPEX advantage as well. If we make comparisons between per ton of ore processed that is required, we're looking at a difference between $60 to $80 on the sensor-based sorting dry process side, and $2 to $2.50 per ton of processed ore on the DMS side. So there is definitely not just an environmental benefit, but also an operations benefit.
All right. Yeah, always helpful to have such a picture that gives a good idea. So the technology that we talk about is sensor-based sorting. SBS, if you want to keep it short, and it can be applied in different ways on mining sites. Can you give us an overview of this?
Yeah, absolutely. So from our perspective, we are driving 5 ways of applying sensor-based sorting. And these 5 ways are, as we've discussed, run-of-mine pre-concentration. This is alleviating the downstream, looking from an upstream coarse gangue rejection perspective. Then we've got final concentration, which is a very interesting topic. Haulage efficiency, and haulage efficiency has to do with reducing the amount of material that has to be hauled from pit or underground to the actual plant. And then we have secondary mining, which is somewhat of a name that has been adapted. It's really looking at stockpile retreatment, where there are stockpiles historically that have been put into place for whatever reason, and re-looking at those stockpiles to see whether there is an advantage to process them or to manage the environmental risks around them. The other is then low-grade reserves, or ore bodies that perhaps are satellite that could be looked at as a potential reserve that could be then introduced as well into the processing plant through a sensor-based sorting plant that may be standalone near that reserve. So those are the 5.
That's definitely an overview. Thank you so much for sharing this. Lots of information for the audience. So could you please explain the most significant 2 for us?
I think for me, what stands out is run-of-mine pre-concentration, because this can be applied in both brown and greenfields projects quite easily, and it's, like I said, adaptive. And we can do this by having a look at a simplified flow sheet. So what we have here, as I mentioned, nothing that is unlike other traditional practices, crushing and screening. And then we have the introduction of the STEINERT KSS system, where we create a pre-concentrate. So this is something that would go further into the plant. And we have the coarse gangue rejection or waste material that can then be stockpiled and managed, because then we know what is the composition, what the grade of that is. So it also provides for stockpile management or waste management. And also grade control on the side of pre-concentration, because we know what we're putting out of the system as well. It's easier to understand. This is important to also point out that from where we would insert this kind of technology within the circuit would be somewhere between the secondary and tertiary crushing circuit. So there's already, from that point of view, the alleviation on energy consumption.
All right. And can you please point out and underline once again the benefits of run-of-mine pre-concentration, so to have it really in mind for our audience?
Absolutely. So numbers were discussed earlier on, and maybe going back to those kinds of numbers, from an energy consumption perspective, we're looking at somewhere around 30 to 34% a reduction in energy consumption by placing the sensor sorters as I've described. And then as a result of that, in terms of water usage reduction, we're looking at a 40 to 44% reduction in water usage, simply because we're able to process dry. And then one aspect that's really, really important that is also under discussed within the industry is fine or ultra-fine waste generation. This is slimes that are problematic for the flotation plant downstream, problematic for the recoveries downstream. And in that case, we can see significant reductions, about 50 to 57% in that sense. So that is really helpful as well.
Got lots of information, benefits for the first application. Can you also take us into the second application?
Absolutely. So the second application for me, this is what we call final concentration, and we have another simplified flow sheet for us to have a look at. Now, the idea of final concentration is nothing new. Its application in the diamond processing industry has been in place for quite a lot of time. The reasons they're behind are slightly different. They have to do with security reasons, but nonetheless, it's proven technology on that end, and it's a proven way of processing on that end. And this thinking has then been adapted slightly differently in our case here. So what we see here is a magnetite hematite ore body as an example. And in this instance, what we are trying to do, or what we have already done in a number of instances with our installations, is generate a concentrate of lump, so a magnetite concentrate in excess of 63% iron. And why that's important is that lump product can then be utilized for direct reduction. And we know that through several discussions, and a lot of what has been of great interest is finding ways to create or to make steel and iron a lot more greener. So green iron, green steel. Yeah. And this is the perfect way to generate a raw material for exactly that. Understanding that not all ore bodies and not all mineralogies allow for it. Liberation plays a key role. However, we see that there's certain aspects, certain areas, and certain ore bodies that certainly allow for that, and we need to take a look at that, at those opportunities. So that's what we've done. In the second instance, then we would have a second concentrate that's generated, and maybe this is where the focus is then on hematite, and that can then be processed through the processing plant, whereas the waste, provided that it is fairly barren, or at least so low grade that it doesn't make economic viable sense, can then be stockpiled or put it together as backfill. So those are the options, and that's what we have put in, tried and tested.
And what I already see is, while you're giving this presentation, questions are coming in the chat, so that's always good to know.
It is very good to see.
Something we come back to in just a couple of minutes. Before, I do have some questions to ask. Would you share with us how the system actually works? So what you just started to explain.
Absolutely. So again, we have a visual. Today we're using a lot of visuals. What we as a company, have reflected on the requirements, changing ore bodies and complex sorting tasks, we've taken on the decision to take a multi-sensor approach to sorting. And it's not an exclusive approach, but it's one that we've seen work very well for a number of reasons. So what you see in this instance is a belt-fed system with a vibrating feeder on the, let's call it the tail end of the system, where material is initially introduced into the sorter. The responsibility of the vibrating feeder is to accelerate the material forward in a monolayer onto the belt. And in this instance, we're talking about particle sorting. So every single particle is analyzed individually, and a decision is made on the basis of that particle. That material is then transported through a sensor area, and we can adapt various different sensors in various different configurations together. So we can have one of the essential sensors. In this instance, we've given the examples of X-ray transmission as well as near-infrared. So one of the essential sensors can then be coupled together with all three or one or several of the secondary sensors that you see there. And in this instance, we have color, we have laser 3D recognition as well, and induction or electromagnetic conductivity. And those can then be coupled into the sensor area. Once that discrimination has been made, the particle has been recognized, the decision has been made to eject it out of the stream, that material is then accelerated over an area where we have got a valve bank. And this is where the pneumatic valves that use compressed air to expel those particles out into the second compartment, which you see there behind the splitter, and the rest of the material falls into the stream. So this explains a little bit what the process looks like and what the machine looks like and what the process idea behind it is.
All right. And in the meantime, questions are popping up. Always a good sign. Let's focus on the sensors once again. So are those sensors individually responsible, can we say that, for characterizing the material's individual responses?
Yes. It's important to point out, I know that I emphasize the multi-sensor approach, but it's possible to just look at single individual sensors and single individual responses and make a decision just based on that single individual response. And I think it's something that we'll have a look at over here in the next video, where we see this is a video that essentially represents material. It is material that has been scanned on a belt, and it is XRT images that you see on the left-hand side in grayscale form. So you see dark images or dark particles and slightly lighter gray particles, and that is just an unclassified raw image of material on a belt. Darker particles represent atomically denser material, and lighter particles represent atomically lighter material. What then happens is within the algorithm or within the classification tree, we then decide on taking those images and making some various comparisons. And that then is on our end. We classify those images and make a decision. And as you can see, there's some images there on the right-hand side, the classified images, where you can start to see different color ramps or colorizations. And that is an indication of what the content of the material is. Also, importantly, it sometimes gives an indication of the structure. So that gives us more information. We can make more decisions on that basis. And so here you can see how also mono or single sensors can be utilized, definitely.
Thanks to Paul for playing the video. It's always a teamwork here, quite near to us. And I know that you did your homework, Lerato. So can you please share one or some concrete examples with us?
It's hard to choose one, yeah, of course. But I think that one that comes to mind that is really, it's a standout because this is a client that has chosen to adopt the technology quite early on, but also has come back and thought about ways in which they can see the benefit, utilize the technology for various different tasks on site. So they have a series, let's say several sorters in series as well as in parallel, and this allows them to create chromite as a metallurgical grade chromite for their use and also for export. But at the same time, they're able to make a secondary product, commercially sellable chromite, at a slightly lower grade. But this adaptation and this configuration within the plant is something that is unique, and this is something that we'll see in a video shortly. Here we see a chromite mine, one of the first installations using X-ray transmission sorting
with over 10 years of pre-concentrating run-of-mine. The client expanded the installation to include 2 further sorters using STEINERT KSS. The STEINERT KSS is fed with particles 1 to 4 inches, approximately 25 to 100 millimeters. The control panel you see here makes it easy and user-friendly to switch between various recipes, depending on the grade and requirements. This customer is able to upgrade their chromite ore to 37%. The latest installation is a stockpile retreatment installation. All these expansions show that the customer trusts the technology and values the benefit thereof.
Always helpful for imagination to have a technology been working in action. So thank you so much for preparing this video. And now we can focus on the question. It's time to have a look at the chat. All right, there's something we have to, oh, that's a long list. That's a long list. Let me see. For example, how many crushing stages are needed before sorting ROM material?
Thank you for the question. So the number of stages, it depends really on the material. So softer materials would probably require almost no crushing, because if a CM, a continuous miner, is able to break that material down, we could have a look at material with a passing size of around 90 millimeters already. In some instances, we're already running the chromite instance, which you saw over there. We're running at 100 millimeters in size. So this is ideally after the primary, but in some instances, if we can sculpt off from the primary and just take the undersize from that, that already is well sized. The other aspect that we have to mention is liberation comes into play. So there are some instances where it's probably better to crush slightly finer, so after secondary, where we can liberate a little bit more and then get that decision making criteria between what we want inside. So if we're looking at veins or at spots versus slightly less dense material, then we would need to have that that contrast, and therefore we would need to liberate slightly more. And in that instance, then of course, it would be after secondary. Very rarely would I say that it would make sense after tertiary, but there's some instances where it might.
All right, thank you for your question. Next one, can you please elaborate a bit more on haulage efficiency? Have sensors been placed underground to reduce the load, the haulage to the processing plant? Quite a long question.
Yeah, I like that question.
Yeah, okay,
yeah.
Cool.
So it's I think what we have to keep in mind here in this instance is what we've discussed today is particle sorting. And there's another aspect of sensor-based sorting called bulk sorting, which is separate from the point of discussion, but has very much a valid place within the discussion around innovation and the clean energy transition. In terms of haulage efficiency, what we have seen is a number of sorters placed underground, where we've also had, let's say, a primary crusher underground and reduced the amount of material that needed to be hoisted up and therefore generated backfill already underground. So that is an example from underground perspective where we're able to actually have the first crushing screening stages happen underground. Material is amenable enough for us to process directly after primary crushing, and therefore can do particle and perform particle sorting underground. And then, of course, from a haulage efficiency perspective, for open cast mines, this would be an input crushing sorting sort of situation.
All right. Let's check the list. Oh, there's really a long one. So I see this one. Is there a recording of yesterday's discussion? Yes, there is. I'll refer to this one later on, how you can find it. And then next one, let me see. You can always also read, for example, what could be the sorting capacity for each fraction is another one.
Mm-hmm. That's a good question as well. Unfortunately, the answer is it depends, but I can give the criteria as to, where it depends or what it depends on. So size range or size fractions come into play. We generally promote a 1:3 size ratio between bottom and top size for sensor sorting. So as an example, this means 10 millimeters as a bottom size means that 30 millimeters ideally would be the top size for that specific sensor sorter. We're flexible slightly and amenable up to about 1:5. And that will just depend on the material. So that's the first criteria, size. The next then is specific gravity, so the density of the material essentially. That plays a role because the denser it is, the more of it is contained on a belt. We have certain widths of belts, and therefore you can contain only so much of a monolayer on a belt. We have to maintain a monolayer. That's another criteria. And then cubicity or flakiness plays an interesting aspect from, so shape plays a role. We have units running up to 200 tons an hour, and we have units running as low as a ton an hour. So that gives you an idea of the range of throughput.
All right. Yeah, and let me mention this. So whenever there is a further question, so when you listening to Lerato's answer, please feel free to contact STEINERT. We'll give you the email address, so because we want to get you engaged and involved. Let me see, what is there? What is the typical compressed air requirement in terms of M3T? You know that? Of sorter? Okay, yeah, makes sense. Of sorter eject.
Yeah. This also depends on the amount of material that needs to be removed. So, and then size plays a role in it as well. So unfortunately, this is an answer that would be, let's say, site specific and application specific. Compressed air is the biggest, let's say, OPEX requirement in comparison to, let's say, DMS and jigging, where with jigs, it would be the water aspect of things, and DMS, it would be the media, the correct media, as well as the water, that would be the cost comparison perspective. But it's impossible to give just one number, because it ranges if you're ejecting only 10% of the material versus 50% of the material, which would be on the higher end. And if you are ejecting very frequently, because you have small particles versus larger particles, which is less frequent. So there's no one number, there's a range.
Okay. And there's another question that I can read out. Would you wash the material prior to sorter?
Yes. This is something that is done primarily for optical sorting. So at the same time, when you have clays for optical sorting, I would say is almost mandatory. So if you have a very clay deposit, very clay ore body with a high clay component, it almost becomes imperative to maintain a consistent surface. Let's say maintain a consistent surface, so that your characteristics also remain consistent, that you can see them consistently. And for this reason, when using optical based practices, so this would be for color and laser, for example, in those instances, you certainly would it would be recommended to have let's say a wash and then a drain and rinse screen prior to sorting. When it comes to X-ray transmission perspectives, as well as electromagnetic conductivity, it's not a requirement.
All right, so a clear yes, and then a very detailed explanation why and how it's happening. Thank you so much for your questions. So all those questions that we weren't able to answer right now, you will have a look at those later on, the experts here at STEINERT, and we'll come back to you to answer all those questions. You can also write them via email once again, and the email address is popping up in a second. Let me just point out this one, because the question appeared here. So if you missed the first session, the first live stream, no worries. We'll make both sessions available on the STEINERT YouTube channel. So please check that out. And for those in the audience that also like to read about the topic, STEINERT, the team, has put together a summary. It is our solution guide, sensor-based sorting for mineral processing, or if you want to keep it short, for pre-concentration. And we will put this one in the chat in this very moment. Thank you to the team. And yeah, I'd like to add this special service. As I already mentioned, we'll have experts all day and also tomorrow to answer all your questions. And please write to mining@steinert.de. And yeah, the team will work through those questions as they come in. Thank you so much, Lerato, for the first live streaming, for today, for sharing all your expertise, your passion, your knowledge. That was a fantastic pleasure. Good to have you. We learned so much about the clean energy transition and Steinert's sensor-based sorting solutions. And now I'd like to invite you to wrap up this live stream here from the studio in Cologne.
Yeah, in Germany.
Yeah.
Yeah, thank you very much. I think my biggest thanks is an extension to the audience. I think it is important for us to have these kinds of discussions, to engage with one another, and to be able to also understand why is it important. I think reflecting on yesterday's session, it gives good context as to, you know, why are the considerations around innovative technologies really important for the transition. And I think that it's also our responsibility to look at the transition in a responsible manner. So I really thank the audience, and thank you, Sebastian, for being a wonderful host.
Oh, pleasure. Thank you.